Okay. Hi, everybody. How's it going?
Good.
How's everyone? We'll just take turns. How is everyone starting from now? They have a microphone here, and they're going to force me to stand behind the lectern. I'm not very good at standing behind lecterns, but I'm going to do my best. I also want to just throw out there, on my way here yesterday evening, I seem to have come down with some sort of a congestion thing. My right ear's not super happy, but I'm a professional, so we're doing this. We have an hour and a half, and I think a lot of stuff to cover, but it should be a good time. And then I'm going to go to urgent care and get all the antibiotics in the world. So thank you all for your time and for your attention. Let's jump in. Obviously, the most important things first. Who here has Twitter? Heard of Twitter? Twitter? Anyone? Twitter? It's 2016. We have Twitter? Okay. So if you have the Twitter, you can interact with me on the Twitter. If you disagree with things I say, if you want to troll me, I prefer it in 140 character pieces. That's what I can handle. But you can certainly throw it out there if you want to. Also, for the live tweeters in the audience, I do have my Twitter handle down there in the bottom, which may be visible. It's really tiny. Email. Email. Anyone? Email. No? Okay. You can, if you have a screed you want to send to me, if you really disagree with me, you can send it via email. The last time I used that joke was today, so we'll go ahead and reset the counter on that terrible joke about email and Twitter. And I do write things on the internet that you can read if you want to at kcwest.com. They do all right. So I happen to work at this company called Pivotal. They do allow me to go all over the place and give talks. I'm very grateful to them that they allow me to travel the world and do this sort of thing. So I feel that it is fair to mention their name, and now we'll move on from that. So this talk isn't really about containers as such. So containers are interesting, and they give us some good advantages and some good opportunities when it comes to scale, repeatability, reliability of deploying and managing applications. But this talk is at a little bit of a different level. I want to talk about operational maturity. I don't really want to focus on a container, because one container is quite adorable all by itself. But I want to talk about how you can build applications, operationalize them using technology like containers, and then manage them. So I'm going to say that you have to be this tall to ride this ride. We're going to talk about a lot of stuff that works at a certain scale. How many of us would say that we handle... let me ask a different question. I like hand-based participation. How many of us here would call ourselves developers or engineers building some application that human beings interact with, you have to deploy, and hopefully it makes somebody's life better? Who's doing that? Cool. All right, that's maybe about half the room. That's cool. And then how many people would say that you're maybe more on the operations side, where you have to manage applications and keep them alive and get the pages and put out those fires and that sort of thing? Who's doing that sort of thing? All right. Maybe about a third of you. So about a third of you are responsible for the fires and the garbage and the terrible things that the first group built that they throw over the wall to you. That's cool. How many folks would say that you're doing the DevOps? You kind of span both of these roles. You have responsibility not just for producing the things that catch on fire, but for putting out those fires. All right, so that's maybe about another third of the room. That's cool. That's cool. And then how many of you are doing this in production? Something that people are actually using. That's good. Okay, good. So you kind of have to be this tall to ride this ride. I think we're all on this ride together. So I mentioned audience participation. How many of us, before you got into this room or looked at the schedule, have heard of containers? Know about them? Okay, how many folks are actually building a container or working with containers, trying them out? How many of us are running them actually in production? Okay, a much smaller percentage, and that's generally to be expected. Just to give a high-level overview, the concept of a container, right, is an isolated file system, a root file system that's isolated. That can come in a couple of different types of formats. And then there's some metadata around that file system that instructs the Linux kernel about how it should run processes that will be run within that isolated file system. and the sorts of constraints that the Linux kernel should place on those processes. It's a pretty abstract concept. These concepts have been around for a while. How many people know when changeroot first came on the scene? Yeah.
I would make an educated guess, but around the 80s.
It's
1982.
1982. So 1979, Solaris was doing, or no, BSD I think was doing jails.
They were first, yeah.
Yeah.
PSD.
Yeah. So, it's been around for a little while, and then the Linux kernel has had C groups and namespaces for a few years. So, we're talking about this in the abstract, right? The general sense. What about schedulers? This concept of a scheduler. Anyone have a lot of familiarity? Yeah?
Yeah.
So schedulers being the idea that you need to be able to schedule work across a set of compute resources. Containers, if you're building and running containers, you can then distribute processes that are running in those containers across a set of computing resources. Anyone heard of this thing called the cloud? You can run it on other people's computers, or you can even run it on your own computer. So the idea of this stuff kind of comes from this idea that you can get economies of scale by consolidation and by taking advantage of things that are otherwise utilities by this point. So having computing resources is kind of a commodity. It's kind of a utility. We get water into our homes. At least some of us get good water in our homes. It's a 2-year anniversary of Flint not getting good water. I think that's nonsense, but it's another topic. We get water, and that's a utility. We pay for the amount that we use, and so the cloud kind of gives us a similar opportunity. You don't have to run it on other people's computers, like Amazon's or Microsoft's computers. You can also have something that behaves and operates similarly on your own computers too. Okay, so some of you may be coming here for this. So this is where I talk about Docker. Docker, 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 Docker. Okay.
You did that with for loop.
Yeah, I could have done that with a for loop, I agree. We're going to move right on. So we're talking about containers in the abstract. I'm not talking about a specific technology. I don't think it would be fair to just have a specific vendor talk or a specific tech talk. Let's make this a broader conversation. So the factors. Who's heard of these 12 factors? Okay, so these are a set of architectural and software design practices. Heroku made them popular. When Heroku has this cloud platformy thing, they made them popular. And they said that if you build software that adheres to these constraints, then your software will run well in the cloud. It'll run well in a distributed environment. It will run well in an elastic environment. And these constraints can be sometimes challenging for us, sometimes unexpected. But if we do adhere to them, then we get the economies of scale, and we get the environment that we build our applications and deploy them into. We get promises out of that. That environment can keep promises about the uptime, the resilience, the capability of keeping our applications healthy if we adhere to these factors. And we're going to walk through them. But this talk is about sort of operationalizing them. What does it mean if you're building containers and you're trying to distribute and manage large numbers of containers of ideally applications, right? So the first one, we're going to run through them. By the way, this is going to be a talk that has best practices and also anti-patterns. I kind of mix them up, and I don't know which ones are going to come first. So either we're going to get really incredulous about ideas that do not work well in distributed environments or with container technology, or we're going to be really happy about things that do. And I think it's going to might be a fun journey. I don't know. We'll see. So the first one is having one code base that's tracked in revision control with many deploys. The idea here being that if you're building an application, you want to be able to have one code base, and when you deploy it into multiple environments, you should not have to augment or modify that code base. So you think about the idea of having maybe a development, staging, user testing environment as well as a production environment. When you decide that you've got version 2.0 of your shiny new application, you should be able to deploy the same exact code base to every single environment without modification. That's the idea here. The beauty of containers is that you have to build a container before you run a container. So it isolates that process, and you want to build an immutable container, a container that isn't going to change. So the idea for a container where you containerize an application is that you can put that application into that immutable artifact, an image, and then you can distribute that image into multiple environments without changing it. So the anti-pattern would be building separate images for staging and production. So if you need to modify your code right now in order to make it run in staging versus production, maybe there's configuration information or databases you want to connect to, feature flags that you want to turn on and off. If you have to do that through code modification, that's an anti-pattern. You should not be doing that. You should have one code base. And you need to find a way to extract that type of customization for your environments into a different form, and we'll talk about that in a second. Another one would be to have different tags for dev and prod. Within the Docker ecosystem, you can tag your images. You should be tagging your image with semantic versions. Who knows that concept, semantic versioning? v1.0.0, v1.0.1, and so on. Those should be your tags. If, again, you're building customized tags in order to customize the container itself for different environments, then that is an anti-pattern. You should not do that. The best practice is to use the environment or use feature flags. So this is, for all you application developers out there, when we talk about the environment, what I think is really awesome about the way technology goes is that environment variables are quite simple. In the Linux space, you have an environment variable. You have a certain environment. You spin up a process. That process has access to the environment it was spun up in. That's the context for that process. It's incredibly easy to access those environment variables with just about every programming language you want to use. And then you can just use them, and you can make decisions about that environment, and you can inject different types of configuration into your running process using environment variables. Super simple. Over the course of years, and I blame all the folks who like to build enterprise-grade software, we've made that much more complicated, and now we have XML files everywhere and YAML files everywhere, and we've got special external services just for injecting environment, and some of that can be beneficial in certain types of architectures, but it's quite complicated. And what I love about this circle is that we're back to saying, well, that simple thing we did 30 years ago with environment variables seems to be working out. So maybe we should just do that simple thing. That'd be all right. Feature flags is one that I want to call out. How many folks build a system that has a feature flag concept right now, where you can flip between two features, A and B, or two versions of a feature, or maybe you use it to turn on a debugging mode or something like that. Feature flags are great. I think they're an excellent pattern, and they're worth pursuing. They do require a certain amount of rigor for your engineering teams, for anybody who's building the software. Building feature flags into your code allows you to have diverging paths for decision making when it comes to whether or not you choose this logic path or that logic path. But the challenge is that more often than not, engineers don't get the opportunity to go back and remove code for paths that are dead now because those feature flags have been turned on and we're not going back. Right? So when it comes to rigor, I really dislike dead code paths in my code bases. And I have found that it can be very challenging to get the time to remove them. But if you do it, the feature flag pattern is very powerful, and it allows you to have very flexible software. And then you can get away even more easily with having one code base and many deploys into multiple environments. Okay, explicitly declare and isolate dependencies is a second factor. You'll note that in green here, I try to highlight words that I think matter, and we've got explicitly declare our dependencies. If you're building and deploying an app, you need to know the dependencies that app relies on. This can be everything from what operating system or distro you're using, to versions of libraries, to versions of third-party tools. You should know everything that your application depends on, and you should have it explicitly declared. A lot of programming environments right now make that kind of easy. So in the Ruby world, you've got a gem file, right? And you can specify all of the gems you rely on, and that's at least one way to make that possible. What I like about building containers is that you have to build up that file system. So you have to build up the runtime environment that your application is running in, and you usually start from a base operating system, and then you put things on it, and they're explicitly declared in code. So that's quite beneficial, right? That's a provisioning step. But also, it's important to isolate your dependencies as well. You shouldn't necessarily package them or bundle them into your application. You should find a way to isolate your dependencies from your application and make that explicit as well. So when you're building a container, you're building up several layers through provisioning routines, and that can allow you to isolate each of those aspects of building that root file system and that runtime environment for your application to run in. So the anti-pattern here is latest. Is saying I'm just going to use the latest version of whatever it is I depend on. How many people do this? You don't have to raise your hand. Best practice is to declare version numbers of upstream dependencies. You should know what version of the dependencies you rely on are compatible with your application. And there are many systems that allow you to have sort of a range of versions, usually on minor, like patch level versions, and if we're talking about semantic versioning. And that's okay as well, but you should understand your risk when it comes to that spread. Do we have a question? I'll take it.
I do. When you talk about risk, the recent NPM fiasco with the, what was it, pad left? What's a good way for dealing with that, future-proofing that, short of forking every single repository that you're depending on?
We'll talk about that. So the question was, when it comes to dependency management, how many folks are building with Node.js using NPM, right? So you might have at least been concerned about the idea that there was a very popular library that disappeared from the repository, and that might have made it difficult for you to build out or scale out or redeploy your application.
Actually, in a few instances of that, it's not just one.
That's right. That's a common example, but that's a more popular, more recent example. We'll talk about ways to mitigate that in a second. So another best practice for container management is depending on base images for default file systems and runtime. So in the Docker ecosystem, one of the things that I like about that mentality, and I think it's the most popular way to build containers, so I don't mind using it as an example from time to time. You start with a base image. So that's usually a file system, right? Or sorry, that's usually an operating system. Maybe it's Ubuntu, maybe it's Alpine Linux. That's my favorite for building containers right now. Alpine is super lightweight, pretty security focused. You start there, but there's still some distance to travel between the application that you're trying to package in a container and the operating system itself, typically. Now, if you're building a binary, like with Go or Rust, for instance, you can pop that binary into a container and run that binary, and that's going to be all right, once you've built it. Or even in Java, if you're building a fat jar, that's a self-contained application. You can pop that into a container and run it. You need fat jars are interesting. How many people are Java developers? Should I go down this path? Yeah, so just quick diversion. You need a JVM typically. There's also a way to build a jar that basically makes it an initd script that's self-executable, which is kind of cool because then you can just say my jar start, my jar restart, that sort of thing. That's pretty neat. But nevertheless, you might need a JVM. But that gets me to my next point, which is the distance traveled between the operating system and your application is the runtime environment that your application needs in order to execute. So when you're building up images, and especially if you're managing a large number of applications, you're going to start with the base OS. Then you need to put a runtime on it. That might be Ruby, that might be Perl, that might be Python, that might be whatever you've got, PHP. It is my recommendation, and I've done this in the past, that if you're managing building containers at a reasonable scale, and especially if you're automating it, you should start with those base operating systems, but then you should build intermediate containers with those runtime environments. So you can have the Java and runtime environment with a JVM on it. You can have several versions using tags, and you should have a Ruby image. And what's cool about that is that whenever you go to deploy your Ruby app, for instance, you can start from the Ruby container as a base image. And then you can just add your app, run gem install, get your dependencies on there, and then off you go, right? So that is my strong recommendation, is to build up these layers. Number 3, storing config in the environment. This one is relatively simple, but when we talk about having one code base and being able to deploy to many environments, you need to be able to have a way to handle divergence. For instance, what domain do we expect to be running on, or what port do we expect to be bound to? What database am I expected to connect to, and what are the authentication credentials and the network information? All of that should be provided on the environment. It shouldn't be hard-coded into your app. So one anti-pattern is config.yaml. If we're building containers, and if we believe in immutable artifacts and immutable infrastructure, then we shouldn't build containers where we volume mount special configuration properties and break the concepts of immutability altogether. This is very common, but volume mounting configuration files into your containers limits their portability, right? It presents certain challenges. So this is an anti-pattern. Another one is properties.xml. That's a common one. I should have put pom.xml up in here as well, but I mean, that's generally acceptable. But if you're putting additional properties into your application through the file system, that's generally ill-advised. Any sort of hard-coded feature flag. If you've got a concept of a feature flag, but you're actually doing it in terms of code paths that are hard-coded, where you need to commit something new in order to change that feature flag, that's a problem. So the best practice is that this one is literally about environment variables. We talked about how simple they are. Just use them. It's super great. It's super easy to inject an environment variable. Okay, how are we doing on time? We're doing all right. I have you until 12:15, right?
Yes, you do.
Yes. So if I had a microphone that I could drop, and this one's too fancy, I would drop it now. All right. Treat backing services as attached resources. So one of these 12 factors is the idea that if you're building an application, and if you're building anything that's not a toy, it connects to something else. It could be an API, a database, a caching layer, a message queue, a mainframe. It could be anything. It's connecting to something else. And it should connect to those things over network attachments. All right, specifically network attachments. So the anti-pattern, this is one of the hardest ones for people to really wrap their heads around and accept. But if we get to acceptance, that'll be good. Is that you don't have any local disk. You should not assume local disk. Your local disk is ephemeral. It will disappear. It will be erased. So if you manage state on your local disk with your applications that you're building and managing right now, you need to find another way to manage that. You can choose S3 if you're on Amazon, or Swift if you're on OpenStack, which has an S3-like interface. You can build an API to another data service and interact with that API. If you don't mind key-value stores and you take great care about the durability of the data, you can use Redis. You can use Mongo. You can use something else. But this one is super important. It's so important that I want to make sure that you understand. So what I did is that I made it bigger. Okay, and then I made it bigger again to make sure that we really understand. This is one of the hardest ones. It's one of the most important when it comes to the portability of a container, especially in an elastic environment. If you have a scheduler that auto-places your workloads in a distributed computing environment, you really can't rely on local disk to any degree of certainty. And furthermore, if you try something like volume mounting NFS up in like a giant cluster, everyone knows who's ever tried that does not actually scale. It doesn't keep the promises of the types of performance that you're looking for, and it has strange characteristics whenever you start doing it at that scale. So what we've learned is to keep things super simple and just don't rely on the disk for anything that you actually want to store as state. Connect to external services. If you have to make those APIs, make those APIs. So connect to networking attached services using connection info from the environment. Most database drivers support the idea of an environment variable called database URL, all caps with an underscore in between database and URL. You can provide that. You can provide that on the environment to a container when you spin it up. And that's, again, super simple to do. All right, strictly separate build and run stages. This kind of gets to that NPM thing. But what I love about the container concept is that, again, you have to build a container, and then you have an artifact that's pre-built. And you have to do that before you run it. All right, so it's strictly separated. If you have a deployment process that muddies the concepts of building, deploying, installing, and running, then you don't have strict separation of build and run phases for your application. And in fact, then the ability to install and deploy becomes kind of challenging because everything is connected to one another. The processes aren't strictly separated. One of the things that I love about mature continuous delivery or continuous integration pipelines is the idea that there are steps along the way, that you have an input, starting, say, with a piece of source code. Then you run your test suite, and the output is whether or not the test suite succeeded, it passed or failed. And then from there, you might build a container if it passed. And the output will be a discrete artifact, a container. And then you can deploy that container, and then you can run that container, and you can keep them separated. And so again, what I like about container tech is that you have to do a Docker build before you can do a Docker run in any mature environment, right? So the anti-pattern is install on deploy. So I come from a Perl background, and I'm chilly right now, but like I'm totally rocking a Larry Wall shirt. This is Larry Wall. And one of the things about the Perl ecosystem is that it's very common that whenever you want to deploy a new version of your app and you're going to update your cpan dependencies, you run cpan install as part of that deployment process. Well, that muddies the water. If you cram your Perl app, though, into a container, which is pretty easy to do, you do the install at build time, and then you have an immutable artifact, and then you can deploy that thing, right? That's more mature. It's a little better. So this one is again, kind of straightforward, but you build immutable images, and then you run those images. 2 steps. Containers sort of force you down that path, and that's a good thing. So this is so painfully obvious that here are some other painfully obvious things, that you should eat when you're hungry, and you should sleep when you're tired, and you should book me to speak at your next event, because this is great. And I probably won't have what appears to be a budding ear infection the next time, so you'll get the excited version of Casey West. All right, so the best practice is to respect the life cycle. So there's a life cycle of containers. It's pretty common. I would say that this is good even if you're not building and managing containers, except for the typo here. You should build, run, and destroy as discrete steps. I would fix this live, but I'm nervous. What's that?
That's it, if you only knew how to repair it.
Yeah, exactly.
You have to find something.
Just pretend that there's an L up in there. All right. Number 6, execute the apps as one or more stateless processes. So stateless is something that kind of trips people up sometimes because, again, if you're building something that doesn't interact with any state whatsoever, it's really just a toy. And none of us are building toys, are we? We're probably building some toys. So you want to execute the app as one or more stateless processes. The idea here isn't about not managing state at all. It's about managing the state, keeping that state external to the running process of your application. So this is sort of a decomposition of your application. It used to be the case that when we think of what an app is, that app was usually a full stack, and we could also usually cram that app on, a desktop machine that we converted to a server and we put into a closet somewhere, and that was going to be fine for the most part, right? And on that server, we would have a database, running, MySQL or Postgres or something, and we would have a web server, Apache, and then, in my case, I would have mod Perl compiled into that thing, and I'd be running my apps as one big stack all together. But what we've learned is that we have to decompose that. So I think most of us by now know you should probably run your database on a collection of servers that you're not running your web server on. And when we talk about a web server, for that matter, we might be talking about API-based back-end services and then front-end services that are typically running in the browser, like JavaScript applications, and we should further isolate those. And we've learned that we should isolate static files and static content from our dynamic content, because then we can get economies of scale out of our static content, because it's easy to distribute those, say, on a CDN or across a larger collection of services. So if we start decomposing these things, what we learn is that the state's going to be managed by backing services that we attach over the network, which we learned that we should do earlier. But our applications themselves contain the special business logic, the unique value that we're creating, the stuff that makes us special. Those applications should not have any state that is managed exclusively internally to those processes. So the reason for this is if you have a process that manages its state within itself and it doesn't It doesn't keep that state tracked in some external service. If that process dies for some reason, and we all know that failure is inevitable and it will die, then you've corrupted your system or you've lost information, right? You don't want that. And the container is a completely isolated environment, and it is ephemeral, as we mentioned before. So the memory is just as ephemeral as the disk. And if it disappears, then it's gone, you know. So we should manage our state elsewhere. So schedule long-running. Oh yeah. So also another aspect of the process is that these processes may be run in a distributed environment across a collection of computing resources. So across a bunch of virtual machines or a bunch of servers. Not necessarily all on one, not necessarily pre-forked from one parent process on one machine, but maybe distributed across hundreds of machines. So one of the best practices is to schedule long-running processes by distributing them across a cluster of physical hardware. This is super important because it can also help prevent a common problem, which is that a developer is working on a piece of software or an engineer is working on a piece of software. They're running one instance of that on their local laptop, and it's working great. And then they deploy it into production, or they have someone else deploy it into production, and you might have 3+ instances of that app. Like, what is high availability? Like, at least 3 instances of a thing is typically like the bare minimum you need for something that you could at least hand wave and say is high availability. And then suddenly the application isn't working, it's breaking. And one of the most common reasons it's breaking is that there's some state management happening in the app, usually in memory. And when you start distributing that over a course of a couple of machines, not only does that break through the individual processes, but then if a developer is taking advantage of something like local disk, which we learned before you should not do, that also breaks when they're running on different machines. So this is sort of a best practice just to make sure that we're being very careful about building systems that can be distributed, especially in an elastic environment. Also, this is just good hygiene if you want an application that's resilient. You know, if you spin it up on one machine and that machine disappears, so does your application. Nobody wants that, right? Except like your competition or whatever. So don't do that. Another anti-pattern is NFS. I'm not really a big fan of NFS, and I haven't really personally had any experiences with a distributed file system or distributed network-attached file system that, at the scale of thousands of machines, actually keeps its promises about performance. So if anyone else has, I will hear about it. I will want to talk to you about it. But the ones that I have tried end up breaking down at some point that doesn't make me very happy. But NFS is the worst one, and it's unfortunately very easy to pick on. So I don't have to say anything more about that. We'll move on. Okay, exporting services via port binding. When we talk about services, these are actually the applications that you're deploying as containers. Your applications should provide an interface over the network. I think we've learned, and I know it's only been a couple of years, but I think we've learned that this new thing called the internet seems to be taken off. It seems to be working out for people. So we should put our applications on the network. And the idea here is to bind those applications to a port. You can't specify the port explicitly within the container, though, because you don't have any guarantees about what port you're going to be offered when your application spins up in a container. The container has an isolated network stack. So you don't necessarily know things like what IP address you're going to have internally. I mean, you know about localhost, and you know about quad 0, the magical IP address that if you bind to it, it says I'll listen on any network interface. But also, you should not make explicit declarations about the port that you expect to be running on. So you can't expect port 80 or port 443 anymore for web services, for instance. Instead, you should allow the environment running your container to use environment variables to tell you what port your application should run on, and then you should just bind to that port. So best practice. This one has a little bit of code. In Ruby, fetch the port from the environment. In Perl, fetch the port from the environment. Here's some Java action. Get the port from the environment.
With a lot of lines.
Yeah, with a few extra lines. That's true. I'm not going to do any ragging on specific languages, but But yeah, there's a little more there. Who's into Rust? Who's been playing with Rust? Anybody? Rust? Yeah? This is getting the port off of the environment in Rust. And that's about it. Just get the port off of the environment. Super simple. And then bind your web service or your TCP server or whatever it is you're running. Bind that to that port. So scaling out via the process model. Well, if we're building stateless processes, then we should be able to scale our application horizontally by spinning up additional processes. And containers make this super easy as well. If a container has an isolated environment, if the process that you spin up as a container is an isolated environment, you can spin up 10 of them and they're all isolated from one another. And if it happens to be the same application, you get that isolation capability between those instances. So you can spin up additional instances, and that's pretty great. That means that your application doesn't have to take over a server anymore. Right? How many people have an app that takes over a server? I've totally done that. Like, you can't not run it on a complete machine. Well, at least you can kind of cram that machine into a container now, right? And then you can run several instances. And why would you want to do that? In order to get efficiency of resource utilization. It's expensive to run applications. If you are running Java, then you need like half a gig of RAM minimum, right? And that can be quite costly over time. But one of the things that containers allow you to do is to pack more applications running on fewer physical resources. So that's why we want that isolation. But we should scale out via the process model, and that allows us to do horizontal scalability with relative ease, especially if we've already built an application that runs well in that container, in that isolated environment. So horizontally scale by adding instances. I throw the word horizontal in there because the word scale all by itself doesn't mean anything. How many folks have had a conversation with somebody where they say, is it scalable? You're like, what does that actually mean to you? It could mean anything, right? Does it mean it handles a lot of concurrency? Does it mean it handles a lot of network throughput? Does it mean, whatever it means? It doesn't really matter. But the idea of horizontal scalability is simply to be able to allow more processes to handle incoming requests or incoming network traffic, incoming load. And if you're building stateless applications, then at least at that application level, you can handle those instances, and the state's going to be managed by a backing service that ideally is also horizontally scaled. So let's see, number 9, maximize robustness with fast startup and graceful shutdown. So one of the benefits, and this is one of the things that I love about the Linux kernel, one of the benefits of containers is that once you build one, spinning it up is incredibly quick. So how many of us work in a virtualized environment where you've got virtual machines you can spin up, right? So spinning up a virtual machine takes a couple of minutes. Spinning up a container can take a couple of seconds, sometimes less. The benefit of this, especially for any application that has network expectations or high traffic expectations, is if you want to respond to more traffic coming in, and maybe you want to make that response be dynamic by spinning up more instances to handle that load, then you can do that with containers incredibly easily because they spin up super quick. So I'm old, so I would say if you get slash dotted, does that resonate for anybody? Yeah. If you get like Hacker Newsed or Reddited or whatever it is now.
Slashdot is still popular.
Slashdot is still popular.
It is.
It is.
So if you get whatever that is these days, you want to be able to respond to it perhaps within seconds or even less in order to not have your application go down or succumb to performance degradation due to that load. So you want to be able to spin up instances of your application quickly. This is why that's important. Graceful shutdown has to do with the idea of not managing state in your application so that if your application instance does die for some reason, it doesn't corrupt your system. And there are a number of reasons why it could die. I never do this, and I know nobody here in this room does, but a developer could write a bug that causes the application to crash under certain situations. Again, I know maybe you've heard of someone who's done that. Also, you could have an application where maybe it did respond to incoming load. It spun up and did horizontal scalability by spinning up a number of processes to handle that incoming traffic. And when the traffic goes away, you want to take them away, right? You want to have that dynamic elasticity. Well, you should be able to just take them away without too much worry. So that's what you need in order to get that kind of scalability and the assurances of being able to handle incoming load, but also be able to roll it back without corrupting your system. We don't actually have to say too much more about best practices or not. Containers kind of give this to you if you're building containers. I suppose there is an anti-pattern, and I should probably put it in a slide. I have done this before. I have built an application that is relatively data intensive, and in order to get performance, one of the things that I do when my application starts to degrade is I might, when the application spins up, I might load into memory a bunch of data that I pull out of the database, sort of a hot cache in memory. And the idea there is that startup. It doesn't matter how long it takes to start up my application. When it's running and serving a request, I want it to serve that request quickly. So why don't I load into memory a bunch of basically dictionaries or hashing mappings of stuff, and then I'll have that in memory. It'll take a little while to do when my application starts up, but then my application will serve requests faster than going to the database or going to some third-party system over the network, right? Have we done this? Sure. Hot loading on start? Well, if you do that, you destroy the ability to do fast startup. If it takes a few minutes to do that hot loading, then you've got a problem. So this is actually one of these situations where you're trying to solve one problem, but you end up creating a different problem, and that can be quite problematic. My recommendation in those situations is to load that cache into a system like Memcache or Redis that your front ends can talk to or that your applications can talk to. That's going to be more beneficial to you. All right, keep deployment, staging, and production as similar as possible. This is something that you kind of get for free again with containers. If you build an immutable artifact, it has your operating system, all of your network runtime, all of your application runtime environment, and your application itself in it. If you use semantic versioning and you tag it with, say, 1.0, anytime you run that 1.0 container, you know you're getting version 1.0. And you know you're getting the same stack within that root file system as every other environment. So then you can deploy your application into staging using similar characteristics as production. So that's good for the container. But you also want to deploy it into an environment that runs and manages those containers that's as similar as possible. So one best practice is to run containers in development. So when we're building applications, we're usually, again, connecting to other things. And maybe you're working on some web service over here, but maybe it needs a few other services and a few other things as part of your architecture. My recommendation to you is to run anything that you're not doing active development on inside of a container on your development environment. So that might be your database and your caching layer and some other backend service that someone else built. Run that stuff in containers. So in the Docker ecosystem, Docker Machine makes that super easy, right? Docker Compose makes it even easier to spin up all the stuff that your application is going to depend on, make it network available, and then you can interact with it. It's super important to do this because your application will behave differently when it's connecting to its backend services over a network versus local connection, where that local connection might even be a sock file, right? Or just connecting to local hosts. And unfortunately, when we run local environments that are distributed and we don't take advantage of complete network stack isolation, I can tell you again from a developer perspective, I sometimes take shortcuts, sometimes unintentionally hard code localhost or even forget to encode connection parameters to backend services because the defaults are good on my local machine. Those things don't work in a distributed environment. That doesn't work in a containerized environment. So run containers for the things that you depend on for the applications that you're building. Run those containers in development. Treating logs as event streams is number 11. Logging, it's super hard, right? You build an application and you do a custom log solution for that app, or you use something like Log4j or something like that. And then the other situation is you might put your logs into some random file in a location that you decided was a good idea, and you're spewing those logs all over the file system. That doesn't really work very well. In a container environment, and part of these 12 factors, the idea is that you should have a very simple logging mechanism. Log to standard out and log to standard error. Because your application is going to run as an isolated process in the foreground when it runs in a container. And if you log to standard out and you log to standard error, then you can build tools or use tools that will read and stream those logs and then put them elsewhere. Right? So it's the simplest thing that could possibly work. Anti-pattern, don't put random log files YOLO'd all over your file system. There's another anti-pattern that I want to put in here, but I would have to curse to really make it stick. But don't SSH into your production environments anymore looking for log files. You should never have to do that. Never, ever. If your application is misbehaving or you want to get those logs, something should be streaming those logs into an environment that you can take advantage of. Something should be aggregating them for you. And the first step...
What would you suggest for that?
Yeah, what would I suggest for that? Syslog, frankly. So when it comes to building the fire hose of logs especially for a distributed system, where maybe you have 50 instances of an application across a few computing resources, if you're spinning up your Docker container, for instance, or any container, and you are logging to standard out, you can attach to those logs, and then you can provide them over a syslog drain. And you can use something like collectd or statsd, I think, to do that. And then if you provide them over a syslog drain, then you can connect that on the other end to something that will consume those logs. In the open source world, the elk stack may do that very well for you. I like the elk stack. Who knows about the elk stack, if I say that? Okay, a bunch of folks. So Elasticsearch, Kibana, and Logstash kind of combined together. And basically you get a nice open source variant of something like Splunk. Who's heard of Splunk? Who can afford Splunk? So there's Graylog as well. There's Graphite, like anything. A bunch of these tools can read out of syslog. So I say keep it as simple as possible and just take advantage of those open formats and open network protocols. Bro. So best practice, standard out. Super simple. Easiest thing that could work. Just log to standard out. It's important that if you do start doing this, that you need to be able to capture those logs. So the conversation we just had around that, you need to have a strategy. There are strategies already built into orchestration tools that sit on top of container technology, such as Mesos with Marathon, or Kubernetes, or Cloud Foundry, which is what I tend to use. All of these things have log aggregation tools typically that will allow you to get your logs from that distributed environment and put them into somewhere, right? So that's good. And finally, run admin and management tasks as one-off processes. So the idea here is to not deploy a special container for that one special admin or migration task that you need to run that one time. So how many folks here, and I've done this, how many folks have written a doit.sh? And then like FTP'd that or SCP'd that into a server somewhere in your environment that has the network access that you need in order to do all of the migration or steps that you need. And then, that's your one task. Well, so sometimes what people do in a containerized environment is they're like, well, I wrote doit.sh, so I'm going to containerize it, I'm going to deploy that, and I'm going to run it, I'm going to execute it. Unfortunately, that creates this special one-off thing that isn't very easy to manage. And I guarantee you that if you wrote doit.sh, you're going to write doit2.sh and doit3.sh. And then, your life sucks. Like that's
that
just...
table.sh, I have no idea what you're talking about.
Sorry, what's that?
I said fix that SQL table.sh, I have no idea what you're talking about.
Exactly. Fix that SQL table.sh. Yeah, exactly. Question?
Are you recommending like a fabric service deployment across images or something that you can push to in production?
That's a good question. We can get to that in a second. So the question was, do I recommend a fabric service that allows you to manage these containers across a large distributed system? We can talk about that in just a minute. So the anti-pattern is to build custom containers for one-off tasks. Don't do that. Reuse application images with specific endpoints for tasks. So let's dive into this. So if you are writing, say, a Ruby app, maybe you're using Rake. Who's heard of Rake? It's like everyone has to have their own version of Make, but it's Make for Ruby. It's pretty rad. If you're doing that, chances are you can write a Rake task. And if you can write a Rake task, then you can write the source code that backs that Rake task. You can write it into your application. You can write it using real classes or real modules with real code that gets checked in and code reviewed and maybe even tested. If you do that, then you've got maintainable code for those one-off tasks. Right? That's a good idea. Do we like maintainable code? Even for the one-offs, it's still a good idea. Do we like peer review? Have we learned that that is beneficial to us? I think we have, generally, as a
peer.
What's that?
Depends on the peer.
Depends on the peer. Yeah, quite right. Quite right. So if you do that, then you have maintainable code. And one of the nice things about running containers is that you can have a default command when you spin up a container. And that default command might be run this web server, right? Run this web app. But you can also run your specific rake task or your doit.sh or whatever you have. And you can run it in and it would be referred to as a short running process or a task. So we have long running processes. These are usually your long running services that you want to generally keep up and running. If they fall down or fail or crash, we consider that to be a problem. And ideally you have some sort of fabric, which we'll talk about in a second, that notices that problem and spins up a new one in its place. But short-running tasks, the only difference is it's the same type of code and same type of isolated environment when running a short-running task in a container. The difference is if it exits, we don't consider that to be a failure, right? It's meant to exit. So that's okay. So this is relatively easy to do. What I recommend is that if you're building a special app and you ever do need to do a complicated migration that requires some custom configuration or custom code, you should build that into the source code of your app. And you should build the ability to run it within the container. And then ideally, once you're done, if you never need it again, you can remove that code from your code base. But you've kept it in a maintainable spot. That's a good idea. So now we got to the end of that. We got through all 12 factors. So now I'm gonna say that we're all cloud native. Who's heard of this concept? Like, this is a new term that people are throwing around. Cloud native is a weird word. I'm somewhat responsible for trying to make this a thing. And just to give you an idea of the definition, because nobody knows what it means, like the very short version is that anything that's old and busted is not cloud native, and that anything that's new and good is. It's pretty easy, right? But the whole point of this exercise, the reason why we might accept these constraints and build applications to these sorts of interfaces or expectations is that we do get repeatability, reliability, and resiliency for our applications. Nobody should really want exciting infrastructure, right? We want it to be boring, repeatable. When we do something that we did before, we should expect the same result. That would be nice. Then we're not crazy, right? That would be a good idea. So this is what we're after. And that kind of goes through the 12 factors, but I have a little more time. And I want to go a little bit higher than just running or building containers and the best practices around building those containers. I'd like to talk about the cloud a little bit and some anti-patterns there. Are we up for this? Okay. How many of us, so when I say the cloud, we talked about this before, and we talked about the fact that like you can have an environment that behaves like public clouds even in your own data centers or on-premise, as sometimes people say. So how many of us have something that is like the cloud, given that definition right now? Okay, so maybe like a quarter of us. How many folks are investigating maybe building things and deploying them to the cloud or have some fleeting interest? Okay, and then how many people don't give a shit at all about anything that might be referred to as the cloud? Okay, I have one person in the back, very brave, that's good. Yeah, I appreciate that. So at least we're interested enough to maybe stick around, that's cool. But this part is actually more like the 5 stages of cloud native, which is modeled very much after the 5 stages of grief. Denial, anger, bargaining, depression, and everyone knows the last one, right? Am I revealing too much about my own therapy? Right, acceptance.
Don't be shy now.
That's right, don't be shy. So let's have a seat on the couch, right? Whatever makes you comfortable. We'll make some ground rules. We're not going to talk about family. We're not going to dig into your history. We're not going to get into any weird stuff. But we will talk about your delivery pipeline, right? That's on the table. We'll talk about your architecture, and we'll talk about your automation, right? So it's one thing to have a container, and I mentioned before I use the term adorable. It's adorable to build a container and think you have a distributed system now, right? People do that, though. They get really excited on the weekend, and then they come back to work, and they're like, I have a solution for all of our scalability needs. But it usually takes a little bit more. So let's start the clock. We'll call this kind of a therapeutic session. So this is usually one of the things that I hear when I talk about the cloud and scalability, but deploying my apps in the cloud is painful. And why is it painful? Why is it hard to manage, right? And I come from a background where, again, like I got a server in a closet, I'm happy, right? So like going to this model is quite a bit different. And we start with denial. Containers are just like tiny virtual machines. So we already decided at some point that for most workloads in most environments, and not all, but for most, virtualized hardware is easier to manage and gives us better efficiency than going to bare metal and racking and stacking servers ourselves and that sort of thing. Like we've generally decided that virtualization is all right. Okay. And when folks are considering building and deploying containers, one of the first things that they do is they say, well, you know, it's an isolated file system, and so is my virtual machine. So what I'll do is I'll just take this virtual machine I have that I'm managing, and I'm often managing through golden images and very special configuration, and I'm SSHing into it and petting it and making sure it's super happy all the time. Well, I'm just going to take that and cram it into a container, and now I have containers. And now, like, we're good, right? And that doesn't really work. A container is an isolated file system, but to run one is to run a process or a process tree. It is not to run a complete server. It still shares a Unix kernel, or sorry, a Linux kernel, I should say more specifically. It shares a Linux kernel with other processes, and you can get some isolation there, but like it's still a little touch point, right? But more importantly, you know, you're running many of them on one host operating system. That is a significant difference from a tier 1 hypervisor. It's a different model altogether. Here's another one. We don't need to automate continuous delivery. I built a container on my machine, so let's just run it in production. So how many of us are working with systems that are maybe kind of complicated, but we still have a 100-point checklist to do a deployment? It still takes a day. It's error prone. Human beings make mistakes. Like, what are human beings good at? Like creative work, right? Creative, interesting things. How many of us like to do the same repetitive task every single day? Like, why would you do that as part of your deployment process? But we don't need to automate continuous delivery. That's for someone else. You know, our delivery is simple. I did work in an environment once where the people who were doing release engineering told me, we can't automate our delivery because it breaks. And I'll give you a moment. Until it stops breaking, we can't automate it. And I sat them down and I said, you know, all right, so what you're telling me is it breaks all the time. I hear that. Like, I'm empathetic. That sucks. It breaks differently every time, right? Yeah, it does. Yeah, what if we made it break the same way every single time? And then we could fix it once, and then it would stop breaking that way in the future. They were like, yeah, I don't think so. And the reason is because they don't trust us, right? The people who have to deploy and manage the software that we engineers, and I've been building applications and building applications mostly in infrastructure space, but I've been building apps for a long time. And so I get this. Like, I build a thing, I think it's perfect. It works on my machine. I throw it over the wall. Yeah. And then I'm like, it's your problem now. I'm gonna go drink. And I've actually worked in environments where the application developers had a deployment or a release party for an application they finished, and they pushed over into the operations folks to deploy. They're having a party, drinking beer, enjoying themselves, while the operations people are trying to deploy it and putting out all the fires it caused because it was broken. Now, the ops folks were still drinking. But that's kind of a problem. We need to automate continuous deployment. This one is the same. This is another bug in my slides. So then we get to anger. This makes us angry. So works on my machine. Yeah. So, you know, I built a system. I run one instance of it. It's working great. And now you're going to deploy it into a clustered elastic environment, and suddenly it doesn't work. Well, that isn't my fault. It works on my machine. That's problematic. Here's another one. Devs just YOLOing shit into production. Why do you think operations doesn't want to give devs the access to any prod environments, right? Because you deploy stuff that doesn't work. That makes them angry. Why would they trust you? It doesn't make any sense. The important bit, though, and this is something that I think that a container tech can give us, is that it gives us a nice, clean interface. And there's a separation of concerns and a separation of responsibilities that's quite nice. But the container build is something that should be collaborative between dev and operations, right? So developers like containers because they can say, well, operations hasn't given me an environment that works, or an environment with modern software, or the version of the library I need. But if I can build a container and cram all that stuff in there, it's just a black box. You don't have to worry about it. You know what? In fact, I'll take responsibility for what's in that container. You don't even have to worry about it. That's the development perspective. Like, this is my way of getting around the idea that it takes operations a little while to give me consistent and reliable environments, right? But on the other hand, operations says, well, I still have to care. What about security audits? What about compliance? What about sensitive information and managing that? What about encryption? Like, how are you handling any of these situations? How are you handling security updates and patching? Who's going to update this container when another Heartbleed or Shellshock comes out? And who's going to roll that deployment out? Well, that's going to be me. Like, I'm going to have to deal with that. So you can't just YOLO shit out there and expect everyone to be happy about it and say, I'll take responsibility, when in reality, the concept of taking responsibility can sometimes be as severe as legal consequences. Right? We have to actually be very careful. So then we get to bargaining. We crammed this monolith into a container and we called it a microservice. So we've got this big, unwieldy app. It relies on the local file system. It relies on a million different touch points to everything else. We have 100 developers or maybe even 1,000 developers banging on it all simultaneously. It takes us, months to get to a point where we have a release. But what we're going to do is we're just going to cram that into a container because that's a hot new tech. And I like resume-driven development, which, by the way, is a term coined by my coworker Bridget Krumhout, who's in the DevOps community. Resume-driven development, I want to put containers on my resume. So we're just going to cram that shit into a container, and we're going to call it a day. Unfortunately, this doesn't give you the economies of scale that you want out of the idea of not just resource efficiency and resource utilization efficiency, but also the ability to decompose an application and manage individual components of it as your team scales, right? You have organization scale that you have to deal with. It's not just about whether or not your application scales and runs well. It's about whether or not you can even build it and manage to maintain it in the first place. So you need to be able to decompose it. Now, containers do give you the opportunity to do that, and here's one reason why. It's through the constraint of network-attached services, network-attached backing services, that if you start to decompose a large application that's crammed together into a series of services that interact with one another over the network, then you can start to find the seams in your monolithic application and decompose it along those seams. And you can start to build very clear interfaces and contracts between those subsystems and give them network interfaces, give them APIs, right? And that can allow teams to start to decompose a little bit. And if they work well together, they can collaborate and actually talk to one another, and then they can build a contract that works on both sides, and that's good. So you can't just cram your monolith into a container and then just say, like, we're web scale or whatever. Bimodal IT. Who's heard of bimodal IT? That's amazing that no one here has heard of bimodal IT. I love this. Sometimes I have to talk to people that we call them executives. And
Craft lovers. Call them craft lovers.
and they read journals or magazines. And so bimodal IT is a thing that came out of an analyst group called Gartner. And if you drink the Gartner Kool-Aid, and the Gartner Kool-Aid are actually like top shelf martinis, but if you drink the Gartner Kool-Aid, then you might have heard of this term bimodal IT. And the idea of bimodal IT is that you have some applications that need to iterate slowly because they have a high risk if you change them. And then some applications that you need to iterate on quickly because you need to change them a lot in order to respond to market needs or because it's a new thing that you're rolling out or whatever, right? The problem with this is that by iterating slowly on applications, by making it difficult to deploy, by making that deployment process cumbersome, by not automating your continuous delivery pipeline, it gets increasingly risky to deploy changes to your application. Changing your application gets hard. the more change you pile up before you deploy. Like the delta between code that's in production and code that's waiting to go into production is your risk, right? That's your liability. And bimodal IT says it's okay for some applications to keep that liability high, and their theory is that it reduces risk. I'm here to say that's garbage. You want to be able to iterate quickly. If you automate your delivery process through continuous integration and continuous delivery, how many folks are doing something like that, by the way? You've got Jenkins or Travis or Circle CI or Bamboo maybe or whatever. Yeah, good. Concourse, yes. Pivotal makes a thing. It's all open source. It's called Concourse. It's pretty fun. So if you're automating that, then you can make developing or deploying small changes to your application easier, right? So you can deploy more frequently, which means that you can keep your risk factor low, and that's good. Bimodal IT gives you an excuse to not have to do that for some applications, and I don't buy it. So what if we create a microservices, but they all talk to the same data source? So when you're starting to build out applications and you containerize them and you're decomposing your application and you're starting to see some benefits there, one of the first mistakes that people make is they say, well, the way to decompose my app into smaller services is that I'll decompose the business logic components, but I'll keep the same giant data store, and I'll just let each of those applications talk to that data store independently. And that, unfortunately, still leaves you with a monolithic application where you've got independent teams interacting with that data completely independently, potentially with different business rules that diverge. And then you've got a mess, because then you've got a central data store where the interface between all of your services is just SQL, right? It's not an actual well-managed interface. I have done this in the past, and I've had to walk back from it. It's incredibly costly to start building applications into your infrastructure that connect to the same data store as other applications. You want a source of truth for a certain amount of data. So if you build a service that manages users or accounts, that service should have complete autonomy to interact with the data for users and accounts. And then any other service that needs information about users and accounts, let's say an authentication system, it should have to go through that user service, through the API that you build. You need to have completely sliced services. So this is a thing that you will find if you go down the path. If someone walks into your office and says, I read about microservices, we're going to make all our things micro, it's going to be magic, and they don't talk about how they're going to handle the data, they haven't thought it through. Depression. We made 200 microservices, but we forgot to set up Jenkins, right? So if you have one or maybe even five, if you have a handful of applications, they're relatively large, hard to manage, hard to deploy, but at least you only have like somewhere between 1 and 5, like a handful of them. If you only have a handful of them, they're hard to deploy and they cause you pain. What happens if you make 200 of them? Then you've taken this small little fire that sucks and you've turned it into a huge fire that sucks even more. This harkens back to automation and continuous delivery. So if you are focused on your architecture and the design practices of your application to the exclusion of automating the delivery of the things that you make into production, then you're not making your problem better, you're making it worse. And the reason you're making it worse is because you're doing what's called a local optimization. Who's heard of that term? Like, who's read the Phoenix Project or looked into lean production systems? So the Phoenix Project is a great book. It's actually a work of fiction, but it's very much a DevOps-oriented book. So it's a book about lean production. And lean production came out of Toyota, or a study of, Toyota and how they build cars. And the idea was, they've got an assembly line. And you start at one end and you don't have a car. And at the other end, hopefully you have a car. And hopefully that car isn't busted, right? Hopefully it's cloud native. Yeah? That doesn't work. Okay. I tried. You got to give me credit. Okay. So on the other end, you want a car. Well, in order to have a car there, it goes through a series of work steps. You have these work centers. They all have to work in coordination and work in concert with one another. Well, what happens if the folks that are assembling the body are doing that much faster than the people that paint the body? Then you pile up work in front of the painters, right? And then you've got all these cars lying around that aren't painted, and you're piling up work in front of the painters. Did that allow cars to get out of the assembly line faster? Did that allow you to increase the production of your cars? It didn't. So what happens if you have developers that are pushing code quickly because they're agile now and they do stand-ups and they sing Kumbaya and, and they're just pushing stuff into master, but what happens if you haven't automated the delivery of that code into an environment? You're just backing up your liability, right? We talked about that before. Are you actually making the entire process of delivering software better? You're actually making it worse, right? So it's very important. It's super critical to get automation into the picture. And furthermore, in order to be able to automate this well, we talked about the idea that building a container should be a collaborative effort between the people who know the most about systems management and system development and the people who are doing application development. It should be collaborative between dev and ops. That's a cultural practice that requires a culture of collaboration. And when I think about DevOps, I don't think about like tools. I don't think about Chef and Puppet or, even containers for that matter. I think about the cultural aspect. There's an acronym you can look it up called CALMS. Who's heard of CALMS? CALMS. It's collaboration, automation, learning, measuring, and sharing. And these are all cultural aspects about how we work together, and that's what DevOps is about. So you have to bring the automation and the right processes, and those processes should be automated, continuous delivery. You have to bring the right culture. I think the DevOps culture is something that we've learned that generally scales pretty well and does pretty well in environments. And you have to bring the right architecture as well. And if you're building large systems and you're trying to manage them at scale these days, decomposing them into smaller services is a good way to go. But if you just do one of them without thinking about the other aspects of how you build and deliver software, you're going to suffer, right? So here's another one. So let's say that we did automate the build pipeline, but we only release twice a year. Why do we do that? To theoretically avoid risk, right? What's your favorite place on Earth? It's probably Bellingham, Washington. I'm from Pittsburgh, PA. That's neither here nor there. But my favorite place, the place that I love to go, the place that I always want to be is production, right? I assume that we all like to deliver stuff and get the feedback, hopefully, that it worked out well. You need to be able to deliver more frequently. And in order to do that, though, you have to eliminate or at least significantly reduce the risk of deploying new stuff. So if you're deploying very infrequently, how many people do have like twice a year deployment schedules, or maybe 4 times a year, once every 6 weeks, right? So it should be that you can deploy anytime the business says, or your organization, if you don't work in a business, but anytime the organization says they want to deploy, you should just be able to deploy. And that could be once a second, or that could be once a year, maybe, but it should be whenever they're ready for it. In order to make that possible, you have to take the people who've been burned in the past by doing deploys, you have to take them and make them feel like a deploy isn't going to burn them again. So you have to have a reliable process that gives you a high degree of confidence that when you do a deployment, it won't fail. And that means continuous delivery and continuous integration. It means building automated tests that you can actually trust, right? And so that whenever your automated tests pass, you really are confident that when you deploy something, it isn't going to fail in production. So it's on us if we have built or managed systems that tend to fall over when we change them. We have to build resiliency into that process and demonstrate that things aren't going to fail when you deploy, right? And so containers can help with that, but perhaps even more importantly, having a good collaborative culture between everyone who's responsible for building and managing stuff that you deploy, and having an automated system for that delivery is super critical. But now we get to acceptance. So what do we have to accept? Unfortunately, I'm out of coffee, and I have to accept that. A little bit more. All software sucks. Right? We just have to accept that it's hard to build great software. It's especially hard to build great distributed systems. It's challenging. But that's the situation that we're in these days. So we have to get around that. Where we have to get good at it. But the stuff that we build, the stuff that other people build, like it's all going to suck sometime, right? And that's okay. But here are some things that we also have to accept. We have to respect the CAP theorem. Who's heard of the CAP theorem? A few folks. So when you build a collection of services and you connect them together with a network, you're introducing the CAP theorem between each of your services. And the CAP theorem says that you can have consistency, availability, or partition tolerance. Right? These are three things that you need in a distributed system. Consistency, that everything remains fully consistent, for instance, a transactional model. Or availability, the idea that it's always as available as it needs to be with a level of service that your customers or your end users might expect. Or partition tolerance, that if the system does break apart, if subcomponents become isolated from one another, that they don't just fall on the floor and completely die, right? But the CAP theorem is painful because you can only have two of these, and one of them will always suffer. Right? So this is similar to your project management golden triangle thing of good, fast, and cheap, pick any two. CAP theorem is even more depressing. Consistency, availability, or partition tolerance, pick two. Right? But we have found through building distributed systems over the course of 30-odd years that this rings true. One of these will suffer, but you should make an educated, smart, intentional choice about which one you can tolerate suffering so that the others can be good. You shouldn't just leave it to chance. Right? So you have to build systems that expect failure, that expect their downstream dependencies to disappear, that expect them to respond slowly. The Netflix does this really well. Who's heard of the Chaos Monkey? Yeah. So they even have Chaos Kong. Has anyone heard of Chaos Kong? They have this whole simian army, they call it. So Netflix has, they're all in Amazon as it happens. So they're all like cloudy as hell. And they have different availability zones, right, mapped to different Amazon data centers. And then different subcomponents of those specific geographic regions. Chaos Kong deletes an entire availability zone in production. So imagine if you have US East and US West. Say you build a system with some reasonable disaster recovery, and you have them in two geographic locations. And ideally you want at least three, right, for high availability. Netflix in production deletes one of those occasionally, randomly, and expects no service degradation, and they do a good job of it. But when things do degrade, like they learn very quickly why and how, because their services start to suffer. But they have an expectation that won't happen, so they build their systems to be resilient to that level of failure. So I would argue that you should do similar things in your architecture. Take your database offline one day and see how your applications respond. Or reduce the capacity of your API services by half and see how your front ends respond.
Start in testing, though.
Start in testing, absolutely. Absolutely. Respect Conway's Law. Who's heard of Conway's Law? All right, so Conway's Law, this guy, Melvin Conway, wrote a paper in 1967. It was released in 1968. And everyone reads to the end and they remember Conway's Law. And Conway's Law states that the systems that we build, the software that we build, its organizational structure or its architecture will map to the communication structures of the team that builds it. So just think about that for a minute. Like go back to, like I know we're here on our weekend to get away from work. But let's just imagine on our day-to-day, or even in open source projects, imagine what it's like to communicate with the people that you work with in order to build something. If you have different teams working on different components, if they never talk to each other, if there's political strife, we call that siloing, right? And the reason that we call that is there's a whole concept called functional silo syndrome. Like that's actually it. Siloing, by the way, like this whole concept, I wondered why we called it that. Like I know about silos on farms or whatever, like that's a thing. But I wasn't sure if that was the rationale for that decision. But it turns out that while we were studying Toyota around lean production and their manufacturing process, which allows us to increase the consistency of throughput through their deployment system. That's what Toyota wanted. They wanted consistency of throughput. There was a study at the same time, this was the late 80s, at Goodyear in, I think, Illinois. And they were studying why Goodyear can't get anything out the door. And they came up with functional silo syndrome in the same year that papers were released about Toyota's lean production model. But the idea there was that each of the individual teams that were responsible for operating Goodyear as a company were more loyal to their local teams than they were to Goodyear's success. They were more loyal to their local team success than to the success of the company. They were, in fact, so loyal it was to the detriment of the company. And so Conway's law states that if you have those types of things going on in your organization, chances are the software that you build will be just as broken. The interfaces won't work. The contracts won't line up. You'll have integration problems, right? You'll have failures at the last minute. You'll be forced to talk to each other and you'll be angry, right? So we have to respect that. We have to think about that and then maybe change the way that we work at work, like the way that we work with each other, right? That's super important. And I know that that's a sort of touchy-feely, but I think it's actually critically important even to, again, building and deploying, managing containers or managing applications in the cloud. I think it's important no matter what, but I think it's especially important as systems grow and an organization, a company, a university, like these are systems. As those systems grow, they have scale problems and new complexities. And we have to think very critically about how that works. So we have to be very careful about it. Another thing to accept is that small batch sizes work for replatforming too. So if you're building an application right now that doesn't run in a cloud-like environment or isn't running in containers, don't boil the ocean, as they say, and try and change everything all at once. You're going to end up with a 4-year project that dies, right? Try to take small components, ideally even components with relatively low risk, build them in containers, deploy them into an elastic environment. Connect them to the existing system, though. Don't just try and do a rewrite. Don't try and do a complete replatforming. And by the way, if you haven't heard the term replatforming, I'm using this where we sometimes would use the word refactoring. But I'm not using the word refactoring because I've used it so much that whenever I talk to product managers and project managers or business owners or whatever, they freak out and run and set their hair on fire. So I'm not using a term that freaks them out because I've used it so many times and not delivered anything that they can see as valuable. So I'm using this new term, replatforming. I encourage you to give it a try. It'll work for at least a little while, right? And then finally, automate everything. Like just literally anything that you can automate, please automate it. Put it into a build pipeline, right? It's super important. Put it into revision control. So time's up. We went through our 5 stages of cloud native. What have we learned? Well, I think what we've learned is that operability or operational maturity is a collection of microservices architecture, DevOps culture, and continuous delivery, especially in the cloud, especially in distributed systems and big systems. And you can't let one of them or 2 of them suffer. You have to really tackle all 3 at the same time. Right, that's super important. So with that, we do have 8 minutes for questions, give or take. If anyone wants to, you can also run away. But we should be friends. We can be friends on the internet. That's what @KCWest is on the Twitter. But we can also be friends in real life, and that's what the beer is, the beer icon there. Any questions while we have time? Yes?
Mine is more of a comment.
Sure.
When you were talking about dependencies, you said that you can put one binary file in and then that solves that. But it's not really true, because mostly your binary would never be statically compiled altogether. So we will have enough dependencies on shared objects.
Right.
And these would have various versions.
That's an absolutely great point, and I can even give an example that I ran into recently. So the comment was, I mentioned that if you're building, for instance, a Go binary, and you want to put that into a container, that can get around some of the dependency management that you might have at install time. And the comment was that that's not always true because sometimes things are dynamically linked, or more often they are dynamically linked. One of the things that people like about Go, though, for instance, is that it is a binary that you can run on any Linux architecture, but it turns out that's not actually the case all of the time. Go still requires a glibc. And Alpine Linux, my favorite Linux distribution, guess what? It doesn't come with a glibc. You can install some compatibility layers. You can install BusyBox, right? You can get around it through a change root jail inside of BusyBox, and I've done that process, and that's fun. But that is a very good point. That just because you build a Go binary doesn't mean that it runs on everything, for instance.
Right.
And without additional consideration.
And the second smaller point that I'd like to make in that regard, even though I think it's the more important one, is that oftentimes people think they can avoid proper packaging by using containers, and they can't.
Right,
in my humble opinion.
That is also a fantastic point. The point was people think they can avoid package management or vendor management by building containers. Absolutely true. I've heard that as well. A lot of folks think that containers automatically give you portability, and that's also not true. A container can run on multiple environments, but if you aren't careful, for instance, about volume mounting or the types of interactions that you allow the container to have with the host system, how many ports you open up, what your network access is like, that limits your portability over time. But the point that you made about package management and vendor management is super important, because just because you're not doing package management or dependency management at install time when you go to deploy a new version of your application doesn't mean you're not doing it. You're doing it at a different phase. You're doing it a little earlier. Doing it earlier can reduce your risk, which is nice. Because if you build the container and it fails, especially if your tests fail after you've built that container and attempted to run it in a test-like environment, then you didn't destroy prod by having an unforeseen vendor issue. That's a great point. Question?
Do you have some strategies for avoiding Docker Compose YAML hell, where you're developing service A, and you've got these other dependencies that you're using the prod versions, and you've got to swap out test doubles and yada yada?
Yeah, so do I have any recommendations for Docker Compose hell where you're swapping between versions and variants of your underlying dependency containers? I don't have a good strategy that I've found that makes that any easier than the existing situation. Maybe someone else has, and I would be happy for someone to speak up. Do you have
How about the NPM library?
Sorry?
The NPM library case we mentioned before you promised to get back to that.
Oh yeah, the NPM library case. So when we talked about isolating the build and deploy phases of your software, this is something that can help you with the NPM case. So one of the issues with NPM was that if say you do elasticity by spinning up machines and installing your software on it, maybe you're using configuration management like Chef or Puppet, where you want to get convergence on new machines, you might be doing that conversion by laying down Node.js, running npm install, getting your application on there. If you were doing that in real time as part of your install phase, then it failed when the leftpad library was removed from npm library, or the npm repository. So containers help you with this because you've already got a pre-built container with your application. So if you wanted to spin up new instances, at least of that version, you can do it without the worry that you're going to have to hit npm to do an npm install whenever you want to deploy. And this could be for just redeploying images you've already built. It could also be for horizontally scaling out your application. So that was a situation that people found where you have an elastic system that responds to incoming requests, but maybe you're doing it at the virtual machine level, maybe on Amazon or something else, and you end up trying to do an npm install and it fails, so you can't build and deploy software anymore. If you already have the container built and it's an immutable artifact, you can spin that up all day long. That doesn't prevent you from the fact that you've got to figure out how to deal with that to build a new container. But at least it doesn't make you suffer immediately for an upstream unexpected event.
Something that I've been wondering about in 12-factor, specifically the environment variables, put your config environment variables. It sounds great, but one thing that always trips me up is secrets. I'm a little itchy about sticking passwords in my process environment where it can be read by any system machine. And even if that didn't bother me, it's still not totally obvious how I get them into the environment safely in the first place.
Yeah, secret management is a pain in the neck. So you need to use a third-party system or another service, basically, to manage those secrets. So Console is a fine option out of the fine folks at HashiCorp. Folks sometimes use things like etcd for that. I happen to work primarily with Cloud Foundry, which is a platform thing that does containers under the hood. It has a secret management capability baked in as well. But basically, you do need to manage that. If you're using configuration management to lay down secrets at install time, let's say you wanted to deploy a new container onto a set of services and you're actually putting those secrets into the file system, that's where you end up with that liability. So you need a tool that keeps them encrypted at rest and encrypts them over the network and makes them available to your applications when they request them. So environment variables can be a simple way to do that, but then you should be running your containers with a tool that injects those environment variables rather than laying them down on the file system, right? So that's one thing. You have to get them from somewhere. So secrets are problematic. You can also use something like service discovery. So, Eureka being common in the Java ecosystem, Consul again being a common tool that people are really taking advantage of now. You can use service discovery to keep those secrets and allow services or applications to register with the service discovery tool and then get the secrets that are available to them. So basically, you still need another thing to handle secrets. And that's a good point, and thank you for bringing it up. We have, I think, time for maybe one more question. Yes?
Okay. You mentioned during your talk well-deserved hate for NFS. From my own experience, we have an application, Dockerized it, and tried to do as little changes as possible, so you're not writing a local disk, writing to NFS server, and it's melting that NFS server. It's that can't cope with the load.
Mm-hmm.
What alternatives could you suggest?
Yeah, so if you don't want to use NFS, and if you don't want to change the architecture of your application in order to minimize the change, where you're not necessarily volume mounting, the two things that I might suggest taking a look at, and again, I don't have a huge amount of experience with them scaling the way that I want to, but I think they work under reasonable load, is Ceph, which is a plugin that you can bring into OpenStack, but also you can run in isolation. Ceph is built by Ceph, and it is open source. You can get a commercial version as well. And then Red Hat runs the project Gluster, or Luster is another variant, but I think Gluster is a little better down the path. So you can also look into that as well, and that'll give you a distributed file system that you can volume mount if you need to. I would take care though about the software design over time, and if you do get that to work reliably for you, that's fantastic. But at the scale of deployments that I've been working with, it ends up kind of falling down for us.
Could also try SSHFS. It's pretty good. I haven't tried it in a very large scale.
Mm-hmm.
It is at least pretty reliable and quite easy to set up.
Right. So
it's worth a try.
So the recommendation from the audience was SSHFS, and I'm just doing that for the recording. But, thank you all for your time and attention. I appreciate it. I'm going to go disappear until the event this evening because I want to sort out my head. But if you have any questions for me additionally, maybe we can do it over drinks tonight. Thank you.